Swayam Prabha. Digital India. Educated India.
Good morning and welcome to this, the lecture number 37 of the course Stochastic Hydrology. Now we are discussing some practical aspects of the data analysis. All the techniques that we have studied earlier deal with the observed data, and when we have observed data, let us say of the stream gauges, we need to do certain checks to make sure that the data that we are using for the analysis is in fact of good quality, it is consistent, and that we can use this data in our analysis to make some decisions. In fact, why we do all this analysis is finally to make decisions on the hydrologic designs, let us say of the reservoirs or reservoir operating policies, or even hydrologic designs such as the capacity of the weirs that we want to provide, the culverts that we would like to provide at certain locations, and so on. So, the analysis is essentially done to make sure that finally, the designs that we make, the engineering designs that we make are representative of the data that we have observed. And therefore, in the last class I introduced what are called as the consistency checks for the data. That means, once we have observed data at several locations, stream gauges and so on, we need to check whether the data series that we have for analysis is in fact consistent with the data series that is available elsewhere at other gauges in the same catchment or in the surrounding catchments and so on. So, essentially we look at the homogeneity as well as the consistency of the data. In the last lecture, we examined typically the methods for data filling. Let us say that you have observed data at a particular location for 50 years and something, and in this 50-year sequence of data, in the 50-year series of data, there may be many values missing for several reasons. Maybe it has been not observed, or it has been faded in the sense that they would have recorded on paper and then for some reason it has faded and you are unable to make out exactly what is the data, or the gauge may not be working during those periods and therefore, there is no data available and so on. Typically, whenever we have hydrologic time series, especially in the developing countries like ours, we may not have continuous records. There may be certain values that are missing, and it is important for our analysis to have a continuous time series of data, and therefore, we adopt the procedures that I discussed for missing of the data, filling of the missing data. If you recall, we look at the dates on which the data is missing and then simply fill it by the mean of the flow. If we are talking about the flow data, mean of the flow for that particular day, using all the remaining years of the data in which data is available for that particular day, calculate the mean of that and then simply fill it. This is the simplest way, and I have also introduced some other more rigorous ways of filling the data in the last lecture. We typically used two different periods. For example, monsoon period we adopt certain procedure, non-monsoon period where the flows are very small in the peninsular region, where the flows are very small in the non-monsoon period, essentially due to the flows are essentially due to the base flow during the non-monsoon period. So, we adopt different procedures for the monsoon periods as well as non-monsoon periods for filling up the data. Once we have filled the data, and now we have a continuous time series available at a particular gauge, in fact, at all the gauges that we are interested in that particular catchment, Then we start the consistency checks. In the consistency checks, we ask the question, yes, we have this time series, how representative is this time series with respect to the time series that are observed in the other locations of the same catchment. So, that is where we do the consistency checks. And like I have been mentioning all through the course, the first thing that we do is whenever you have data, plot the time series first of the data and then do the statistical analysis. Simply look at the mean, standard deviation, coefficient of variation, and then you look at the skewness coefficient and so on. Simply get the statistics of the data. The statistics of the data is telling you the story of what has happened at that particular location, how variable the flows are, what is the maximum flow that you can expect, what is the minimum flow that you can expect, what is the mean flow for a long period of time and so on. So, this is we have to keep this in mind when we are doing the analysis using the stochastic hydrology methods. We have to keep in mind that we are relying all our decisions on the data that has been observed, and the data that has been observed at a particular location in fact tells us what has happened at that particular location. It tells us the story of the processes that have happened there, and therefore, we must respect the data, observed data. At the same time, we must make allowance for the errors in the data collection, errors in the data itself, the non-reliability of the data, the bad quality of the data. We have to make allowance for all of these. We must have some rigorous methods of doing all of the making allowances for all of these and then use the data. This is an important aspect, and therefore, I keep on stressing this, because in practical applications simply we pick up some data that is provided by the agencies or the custodians of the data and then start analyzing. The first thing is you suspect the data, whether the data is of good quality, the data is reliable and so on, and therefore, it is important for us to make rigorous checks on the data that we have obtained with respect to the data that is available elsewhere, and then may proceed with the analysis. The consistency checks that I introduced in the last lecture are typically looking at a particular gauge. Let us say that we have two gauges, this is a stream flow, and then there are two gauges, let us say gauge A and gauge B, and the flow direction is like this. So, if you want to check the consistency of this, remember the flows that are recorded at the site B are the flows that are contributed by the upstream catchment up to this point, and the flows that are recorded at gauge A includes the flows that are recorded at gauge B, and therefore, it will have this particular catchment. So, the flows at A must be greater than or equal to the flows at B, and typically they will be this flow plus all the intermediate catchment flow that has not been recorded by the flow B, flows at B. So, typically this is the intermediate catchment flow that comes in. And therefore, if you plot a let us say double mass curve, in the sense that flows at this location with respect to the total aggregated flows that have been recorded at B, you must expect a straight line, and typically the flows at A will be the cumulative flows at A as time progresses will be greater than the cumulative flows at B. So, this is one analysis that we do. I will demonstrate this with a particular case study. Now, if that does not happen, what does that mean? Let us say that the flows at A, I represent it as y A, should be greater than or equal to let us say y B, if I represent y as the flow. If it does not happen, that means if y A is not greater than or equal to y B, what does that mean? It either means that there is something wrong with the data that we have observed at A, or it may mean that you are using a lot of water between B and A, and this is going either as losses or for utilization. Let us say that you have a major lift irrigation scheme between B and A, and then you are continuously using the water at that point, and then the intermediate catchment is not contributing enough to account for the utilization. Then it is possible that the flows at A are not in fact equal to in fact greater than or equal to flows at B. If this is not the case, or if you are not able to account for why the flows the fact that the flows at A are not greater than or equal to the flows at B, it means that there is something wrong with either our recording or our way of measurement itself, and therefore, you must suspect the inconsistency in the data. The other part that I mentioned in the last class is what are called as the specific flows. Now, this is a concept that we often use in India for checking the consistency when we are talking about large water resource systems. Let us say you are talking about a catchment of the size of Narmada river basin or Mahanadi river basin, lakhs of square kilometers of the area, in which you will have sub catchments which will which may all be considered as hydrologically homogeneous regions, in as much as the way they respond to rainfall in terms of the runoff generation. These characteristics are the same across the sub basins, and therefore, these sub basins can be treated as hydrologically homogeneous. If a catchment is hydrologically homogeneous, it means that the specific flow or the flow per unit area that you get for a particular rainfall must be the same across different sub catchments. If let us say sub catchment A and sub catchment B are hydrologically homogeneous, it means that the flow generation characteristics of the catchment are the same for both these catchments, and therefore, the specific flow, which is the flow per unit area, must be the same for both these catchments, and that is what we check in the consistency. So, with this now we will progress and then look at certain examples of what we mean by consistency of the data with respect to the mass curve as well as with respect to the specific flows. The specific flow is expressed as flow volume per unit area of the catchment. So, simply look at, let us say a particular gauge, it has recorded a certain flow, and you look at the annual average flow, let us say, and divide it by the catchment area. That will give you the flow volume per unit area of the catchment, and therefore, it will be typically in the depth unit or cubic meters, million cubic meters per square kilometer of the area. In that area, in those units, the specific flow is expressed. Now, as I said, the specific flow is in fact representative of the catchment's response to precipitation. There is a precipitation occurring, how much of this precipitation gets converted into runoff is what is given by the specific flow. So, it is in fact the response of the catchment to an input that you are providing, hydrologic response. Now, if a number of gauge stations are located in the same hydroclimatic region, as I said, hydrologically homogeneous regions, then you must expect that the specific flows are comparable. This again I have told in the last class, but because it is an important concept, let us again recall this, what I mean by that. Let us say that you have two regions like this. There is one catchment here, the flows are taking place here, and then you have recorded the flows here at this point A, and this is a catchment that is contributing to the flows at bay A, and then there is another hydrologically homogeneous region to this catchment, and you have recorded the flows at B. These two are different catchments, Now, if these are hydrologically homogeneous in the sense that their responses are the same to a given precipitation, then the specific flow at B, which is the average flow divided by the total area of this catchment, must be comparable to the specific flow at A, which is the average flow that is recorded at this location with respect to the catchment area divided by the catchment area. Now, typically we do this when we are analyzing large water resource systems, where there is one gauge here and there is another gauge here, and maybe perhaps you have another gauge here like this, and the flow directions are like this. Let us say this is the flow direction. Now, we compute the specific flow at this location with respect to the catchment area of this particular gauge. Similarly, we compute the specific flow of this with respect to the catchment area of this gauge. Let us say we call it as A, B and C. Now, the C will comprise of this entire area. These borders are coinciding here. So, C will measure, the gauge C will measure everything that is measured at B, everything is that is measured at A, plus the intermediate catchment flow between these locations. Now, when we compute the specific flow at B, we take the flows at this and take this area and compute the specific flow at B. Similarly, specific flow at A and specific flow at C. The areas are different and so are the flows at all of these locations, but the ratio of the flows to the areas will be approximately the same if they are hydrologically homogeneous, which means that the precipitation pattern is the same in all the three catchments, as well as the land use patterns are the same, the vegetation is the same, the amount of urbanization that has taken place in these catchments is the same, the type of soils is the same. In other words, the complete gamut of the hydrologic variables that contribute to runoff generation are the same for all these catchments, in which case the response of these catchments will be the same for a given precipitation pattern, and then we say that these are hydrologically homogeneous catchments. If they are in fact hydrologically homogeneous catchments, then the specific flow that we compute at this location must be the same or must be comparable. Ideally, it must be the same as this, but at least it must be comparable to the specific flows computed at these locations. Let us say that the specific flow computed at C is much higher compared to the specific flows at A and B. Let us assume for the time being that the specific flow at A and specific flow at B are comparable, and therefore, there is a good reason to believe that the precipitation patterns and the hydrologic responses of these two catchments are similar. However, the specific flow at C, which represents this entire area, and typically it accounts for this intermediate catchment area, which is not covered by both this A and B. If that specific flow is much higher compared to the specific flow at A and B, what does that mean? It means that the intermediate catchment here, let us say that I show this by some, let us say all of this has been the intermediate catchment flow. In fact, these two are adjoining with each other, the entire flows are captured by A and B. Now, if the specific flows at C are much higher compared to the specific flows at A and B, it means one of the two things. It may mean that the precipitation pattern here, the precipitation values are much higher in this intermediate catchment compared to the precipitation patterns here, and therefore, for the same hydrologic characteristics of the region, you are getting more flows at this location, more observed flows at this location. Or it may also mean that the precipitation patterns may be the same, but your catchment characteristics are such that for the same given precipitation it is producing a higher inflow, higher flow at this location. If your recorded data is correct, then it means one of these two things. One is that the precipitation values are much higher here, or that the hydrologic characteristics are much different compared to these other two catchments, and therefore, it points to a non-homogeneity of this catchment compared to the other two catchments. So, these are the tests that we need to do for checking the homogeneity and the consistency of the data at that particular location. So, we will go back to the example and then see how these values look. Now, we compute the annual specific flows. Typically, when we are doing large scale systems analysis, water resource systems analysis, we look at the annual flows and then compute the specific flows. So, let us say 50 years of data is available, annual data is available. You take the annual average flow and then divide it by the area of the catchment, you get the annual specific flow. This can also be done for seasonal flows. Let us say one season, monsoon season and non-monsoon season, you can compute the specific flows. Now, as I have been mentioning, the specific flow is useful in comparing the runoff per unit area from different sub catchments within the larger catchment. And the units are typically million cubic meter per square kilometer. This is a measure of the annual average runoff in depth units, typically in meters or centimeters or some such thing. The example that I have been showing in the last class, this was I was talking about Narmada river basin. This example has the average annual rainfall varying between 700 millimeter to about 1650 millimeters. As you go from east to west, the rainfall is varying significantly. And therefore, for large river basins, as the rainfall patterns are changing, if your hydrologic responses are the same, then you may expect different specific flows for different sub catchments. Let us see how it looks like. So, this is a system view. It may not be very clear, but do not worry about it. It only shows there are large number of gauges, stream gauges. These rectangles here, small rectangles, they are stream gauges. And this is the Narmada river. This is Amarkantak here at this point, and this is the Bargi reservoir here. Then there is Indira Sagar reservoir here. There is Maheshwar reservoir here. There is Sardar Sarovar reservoir here, and so on. And there are large number of gauges, in fact 55 number of gauges at which the flows are recorded on all of these. The available record at these gauges varies from as few as 5 years to the length of the record varies from as few as 5 years to as high as about 40 years, 50 years and so on at several locations. And we have to make use of this data to arrive at decisions. Let us say that you wanted to put another reservoir somewhere here, or let us say that there is an ongoing reservoir for which you want to develop operating policies, in which case you have to analyze how the flow pattern has been at that location. And therefore, it is important for us to check. Let us say for Maheshwar reservoir, there is a gauge Mandleshwar. Now, the Mandleshwar gauge at this location, if I slightly zoom that or draw a zoomed picture here, this is Mandleshwar at this location, and then there is another gauge here. This is Mortakka and this is Maheshwar, that is Mandleshwar, which contributes to Maheshwar reservoir. And then there is also another small stream that is coming here, and there is a gauge called Kogaon. So, just focus on this Mandleshwar gauge now. Now, this has a intermediate catchment between Mandleshwar and Mortaka, between this a very small intermediate catchment, and also between Kogaon and Mandleshwar. So, we look at the catchments for Mandleshwar, catchment at Mortaka, catchment at Kogaon, and compute the specific flows, and because they are quite close to each other, because they belong to the same sub catchment, and if we can reasonably assume that there is hydrologic homogeneity in terms of the response of the catchment sub catchments, then the specific flows at these locations must be comparable. Similarly, you look at let us say Sardar Sarovar reservoir. Near Sardar Sarovar reservoir, just upstream of that, there is a Rajghat, which is a stream gauge. Then there is also Tikola, which is coming from the side here, and then immediately downstream of that there is a Garudeshwar stream gauge. So, you will have records before this reservoir came up, you will have records in Garudeshwar, and then you also have records after the flow has been obstructed by Sardar Sarovar reservoir. We will see what is to be done with the reservoirs and how to compute the normalized flows subsequently, but assume that you have normalized flows. By normalized flow, I mean that the effect of the reservoir has been taken out and the flows have been converted into naturalized flow series. So, if you have flows at this location, flows at this location and flows at this location, you can examine the consistency of the data